next step is to take the second law, which we have just written, that is delta H of the system minus T delta S of the system less than 0 for a spontaneous change. And what that does is that it sets us up to introduce the most important variable in all of thermodynamics, and that's the Gibbs free energy. And the Gibbs free energy is represented as G equaling the enthalpy H minus T times the entropy. So if I take delta G and I write this for constant pressure, that's equal to delta H, and then I can write minus T delta S if I also keep the temperature constant. Delta G is equal to delta H minus T delta S. That's a statement of the second law of thermodynamics via this new variable that we've created called Gibbs free energy. And that means that if delta G is less than 0, delta H minus T delta S is less than 0. But let's look at what this means on a chemical reaction coordinate. So in this diagram, we're plotting free energy on the vertical axis, and on the horizontal axis, we're starting with reactants. We're allowing them to go to products, and as we will see, this process can proceed from left to right or from right to left. But let's see what this means in terms of Gibbs free energy. Let's suppose we're starting on this surface of Gibbs free energy at some initial point, I, and we're proceeding through a final point, F. So then I can write that delta G is equal to G final minus G initial. But look what that says. G at I is larger in magnitude than it is in F. That means that G sub I dominates, and this must be less than 0. And indeed, that's what happens. This reaction is spontaneous, coming in from left to right. If I start with pure products, and I engage in exactly the same logic from an initial point to a final point, I discover that delta G is less than 0 on this side of the Gibbs free energy surface as well. That means that the reaction will indeed proceed now from right to left until a particular point is reached, because at this point the slope, delta G, is in fact equal to 0. And that is the point at which equilibrium is reached. And as we will see in the next chapter, there's an entire subject called equilibrium chemistry, and it's based entirely on the surface of Gibbs free energy. So we've made a huge step forward now. We have drawn out of the simple statement of the second law of thermodynamics not just another thermodynamic variable, but the most important thermodynamic variable, Gibbs free energy. And we've related it to spontaneous change. So let's look quickly at a restatement of the second law in terms of our new variable Gibbs free energy. If, and only if, delta G is less than 0, then the reaction is spontaneous. A spontaneous reaction turns out to be extremely important in a practical sense, because the distribution of fixed nitrogen globally to increase the productivity of agriculture is dependent almost entirely on one reaction, and that's the Haber process converting nitrogen and hydrogen to pure ammonia, because plants cannot use nitrogen as N2. The triple bond in N2 is so strong that it's not available. But in the form of ammonia, the bond between nitrogen and hydrogen is much weaker, and the creation of ammonia from nitrogen and hydrogen turned out to be the most important point for feeding the world population. But this is a perfect example of Gibbs free energy, because if we start with pure nitrogen and hydrogen, that reaction proceeds spontaneously. That is, delta G is less than 0 as we descend down the free energy curve toward the equilibrium position. But equally true, if we start with pure ammonia, we also move down spontaneously that surface of Gibbs free energy until we reach the equilibrium state. So it turns out that controlling this reaction, controlling the pressure, controlling the temperature, controlling the iron catalyst on which the reaction takes place, emerged in the early part of the 20th century, and it revolutionized agriculture. So back to the statement of the second law. If delta G is less than 0, the reaction is spontaneous. If delta G is greater than 0, then the reaction is non-spontaneous. And by that, we know that if we've reached the equilibrium point, that reaction is not going to climb back up the free energy surface in either direction. It's locked at the lowest point in the Gibbs free energy surface, which is the point of equilibrium. So finally, we have if delta G is equal to 0, then we have reached the point of equilibrium. And it should be pointed out that while the relative concentrations are not changing at equilibrium, the reactions are proceeding both forward and backward, but they balance exactly. That's what a chemical equilibrium means.